Now let's see part 3, Spliced Precast Girder Tendon Definition. In this chapter, we are going to talk about the tendons defined in our model. Here we have one first tendon installed on stage 03 on segments 2 and 4. It corresponds to a post-tension tendon placed at the top of the girder to control the stress state at the top fiber. After the pre-tension tendons of the ends and central segments, the drop-in segments, the pre-tension tendons 111 to 113 at the first level of pre-stress, and the 121 to 123 at the second level. And it was installed one total normal pre-stress force of about 995 K. After casting the closure pores, it's installed the first continuous post-tension tendon on the eye girder. So at the right image, we can see the first continuous post tendon and its profiled geometry. And at the left, the tendon losses and the pre-stress force installed on the girder. Then it's cast the first deck slab sequence decided by the middle span and the zone over the piers, and it's installed two more continuous post-tension tendons, now on the composite section, the tendon 104 and 105. It was also installed one more tendon on the slab, the tendon 201. After the extreme deck slabs are poured, it's installed one more and last post-tension tendon, the fourth continuous tendon, the tendon 202, and the total primary forces installed on the composite girder are presented in this slide. So we can see the normal force Nx and the bending moment Mz for primary results. The total normal pre-stress force installed on the composite eye girder at the middle span is about 4,130 kips. So let's see the next video about how to install one post-tension tendon in RM Modeler. So in Modeler cross sections, we have defined some geometry points for tendons positioning. So it's the green dots that we are seeing in the screen. These points are placed in a reference set and are, after each one of them, assigned to the part element where they belong. So in this case, we see that the part element that the selected tendon belongs is to part 1. So by editing the tendon point information, we can look at the variable name associated to this point in geometry distance. So we can open the window and select the point T12 in this case. So it's easier to work with variables. Once it became necessary to change the tendon position for stress or capacity verifications, we can go to tables and formulas and modify the values introduced, update the model, and run it again. So in the tables and formulas is where we define the tendon parabolas for the tendon elevation along the bridge development. We can see results in a graph or in a table of values. In main girders, we need to associate the tendon variables to the girder segment elements. So that is what we are doing now, applying the function to all the elements of our girder. So now we can go to tendons and create one new post-tension tendon, the tendon 301 for exemplification. So it's necessary to specify the tendon number, the type, in this case internal for post-tension tendons, apply the material, specify normal for curved tendons, and go to the additional parameters. In additional parameters, we insert the tendon area, the duct area, the friction, and the incidental deviation angle for pre-stress losses calculation. Apply tendon to part 1. In this case are the girder elements, and select the start and end point stations, as the tendon can be equal or shorter from what was defined in tables and formulas. In geometry, it's necessary to insert the main point stations. So what are the main point stations? They are the locations where the tangent is null, where the tendons has the inflection points. So these point stations will correspond in this example to the middle span of the extremes and central span, to the top of the piers, and to the inflection points at each span, where the tendon curvature changes. So that is what we are doing here. So this tendon is referred to one cross-section point, as we saw before. So we don't need to specify the tendon elevation, since the program already knows the variable name associated to this point, the point T12. Okay, we just need to insert the tangent 0 at the respective point stations. For the tangent values, it's necessary to specify the tangent nulls on the vertical plane through the tendon profile for alpha 1 inputs, and in plane or through the transversal direction for alpha 2. So it corresponds to the real tendon geometry. So here in RM, we are always defining the real tendon geometry. So we can display the plan, the profile, and the side views for checking the information introduced. So some more questions about tendons. What type of tendons can be used in RM? RM bridge can handle with all of the 3 types of tendons: the internal tendons for post-tension tendons, the pre-tension tendons, and the external tendons. So for internal and external tendons, exists also the possibility to consider them grouted and not grouted. So the user has the possibility to study the 2 types of behaviors. Difference in tendon profile from InfoTab and InfoPlot comment. This type of issues is mostly related with the restraint conditions for the tendon points geometry. The user needs to check where to place the inflection point and the alpha angle values introduced with 0 and free. So the vertical angles should be free instead of value 0 in the descending and uprising regions to allow for a smooth decrease and or increase of the angle values when the program is calculating the tendon's parabolas.
Thanks for watching. If you found this video helpful, please give it a like and share it with others. If you want to see more like it, please consider subscribing to this and Bentley's other channels. Thank you, and see you next time.